Hello everyone. So if you really want to pronounce my name, it's pronounced Peter Szilágyi, but Peter is really fine, so don't struggle with it. I'm from the following institutions, I won't read them all. And basically, Iris is my PhD, is, so that's what I would like to present. So in short, just a short introductory. Yeah, just switch to the other window. Cool. So my problem with basically the way I started out my PhD was with this simple line that distributed services are complex, or if I want to rephrase it, programming distributed systems aren't trivial. The reasoning are, well, there are multiple reasons. You can pick fault tolerance, or you have a shitload of errors, sorry, that can happen. But the other thing is, which makes it really hard, is that even during normal operation, you have quite a lot of difficult issues. For example, load balancing or scaling out horizontally. And these were the topics that I really wanted to solve with Iris. Now, I was thinking what to present exactly, the details of how things are implemented in Iris, or more like a tech demo. Since we're at the Open Source Conference, I decided that it would be better to showcase Iris, and then if you really feel that you would like to know more about it, then there's plenty of papers on the website. So, what is Iris? Well, Iris is a decentralized messaging framework for backend services. So important things to highlight there are the backend services part, because so usually if you have a nice distributed service, not necessarily backend, then usually you have some messaging middleware in there to help all the communication. You won't whack at it with the standard TCP. Usually your messaging middleware of choice will depend on your use case. My use case was services, so I really tried to focus on them and to take advantage of the features of the backend services. Which means that the things that were important for me is that it should be completely decentralized. I didn't want any single point of failures. I wanted it to be secure against passive and active attacks. What this means is that I wanted to be able to run multiple services within the same network without them being allowed to interfere with each other. You'll see that I say that it has a nice simple API, and it's quite fast. So what makes it different from all the other messaging middlewares? I think about AMQP or ZeroMQ or the likes. Well, there's a very simple concept, and that is that I removed the concept of individual instances as being the smallest building block of a network, of an application, meaning that you don't have a single web server A and web server B and web server C. Rather, you have a cluster of web servers. I don't care whether there are 100 web servers in there or 0. It's just web servers. And this is really nice because it really simplifies things. Now, let's get down to, one more slide. Forgot about that one. So, so we have this nice model where we have clusters communicating with each other, but how can they communicate? What can they do? Well, you have the usual suspects, basically broadcasting, request reply, audition, subscribe channel. The tricks in them is that request reply, so normally if you would have a request reply model, you would have the client which would request something from a server replies. If you have multiple servers, then you can add a load balancer. What I actually wanted to do with Iris is that, for example, I don't know where my mouse is. Yeah, there. So if I have my web browser which is issuing a request to web servers, then let's suppose that the greens are the web servers. I want any web server to reply. I really don't care which one replies. Figure it out, reply. And I don't want to work with load balancers. Just remove them completely. And sorry, this was the request reply. I was pointing to the wrong one. Basically, the green ones are the web servers, and first request goes to the right web server, the second request goes to whatever bottom left. So this was the request reply. Broadcasting is the same, that I want to broadcast a message to all web servers. I don't want to care about load balancer, just web servers go. Now the publish subscribe, you probably know, I don't have to talk about it. And the tunnel, well, many times if you have a networking application, usually if you use only messaging, then sometimes you will shoot yourself in the foot that unique transaction, so you can make sure that multiple messages get to the same instance. And that's when you will need the tunnel, so that you can build a tunnel and then you have a nice TCP-like connection. Okay, but actually, how do these look and work in the real world? So since we're at this conference, let's see some demos. Well, the first demo, I have 4 demos for you, for each communication primitive asynchronous demo. The first one is that let's say that you have 6 people who want to chat. Note that we are in the same network environment. So if these people want to chat, then simple IRC chat room, just log into the chat room, send a message, everybody else gets it. Really, really simple. So how you could do this with Iris, simple, is that, for example, so I will showcase Go code. Single line, which you will connect to the Iris network. Just forget about this number. I'll tell you about that later. We just connect to the Go dev room lobby and create an echo service that will handle our requests, handle our messages. And the echo, what it does is that whenever a broadcast arrives, print line, just throw it out to the user. And then after I connect it to the Iris service, what I do is that I simply broadcast every second. I broadcast the message to the Go dev room, and it will just be an incrementing counter. And if I run that code, then yeah, obviously I'm getting the messages as we expected. Now if I were to start a new window or a new tab with the same code, then let's replace this one with, I don't know, make it Bob. I don't have any better ideas now. And run it, then okay, our messages are intermingled between each other. So the communication is nice and working with these really just 3 main lines of code. And you have broadcasting up and running. And if I were to close this window, for example, now, then and scroll down this way, and yeah, my previous message will have, so I don't get Bob's message anymore. So this is really, you can have a broadcasting, and this really works for arbitrarily many, I haven't tried for too many, but it really works nicely with larger networks. So the main point is that in order to join the network, I can just simply use a connect and start broadcasting away. Now if I want to do request replies, let's see that I have a web browser, and I want to issue request to web servers. Those can be fancier, because, so what I want is basically a web browser issues the request, web server replies, but I want automatic load balancing between them. This is not so trivial if you use a normal networking component. Let's see how you could do this with Iris. Well, okay, now I have 2 separate source codes. One is for the web browser, one is for the web server. They are very similar. What the web browser does is we have the connection code as previously. Oh, I forgot about it, that we're connecting with the browser as a browser. Maybe I didn't detail that too much previously. And I have a request function. I just start requesting every second. I issue a request. I just tag the request with the request ID, issue the request, and whenever something comes back, if I have an error, then I print the error. If there isn't any error, then I print the reply. And I just sleep and repeat. If I run this, then obviously I'm done. And I didn't detail that. Yeah, this the resolution is too short, so the graph there that we did, I put there a 1 second timer for the request to be answered. So if I just run this, then obviously I don't have any web servers running, so my request will be timing out. But if I start some web servers, before the second code, very simple. I just connect to the Iris network, connect as a server. I assign my server an ID. So this code is so ugly so that each of my servers will have a new random ID. And what my server does is has a handle request method. Whenever a request arrives, I just insert that ID into the reply and echo it back. So a really simple echo service, so to say. And if I run this one now, so what it does is connect to the network and wait for requests to arrive and reply. Don't do anything else. And if I run this, then yeah, waiting for requests. Add back the previous one. And down here, So my 57 web server number 57 is accepting replying. Okay, so this was getting a simple request, so getting one web server to reply. But what would happen if I would start? I have to do something. If I would start 3 more web servers to run it, run it. So up here now I have 4 web servers running. If I switch back to my client, my browser, then I have basically all my requests are being load balanced between the running web servers. Note the client doesn't have a clue how many web servers there are. The servers don't know about each other. Client doesn't know about the servers. So what the client says is just semantically one web server reply. It is the job of the system, the framework, to figure out who to reply and when to reply, how to get that request to the web server and for the web server to reply to that request. So that was, and if I think died, yeah. If I were to run it again and then start running off the web server, okay, stand up. So what you have just seen here is that a web browser talking to a cluster of web servers without having to actually set up anything. So 0 configuration, not working. So that was the request reply. And one of the fancier things is publish subscribe model. I wanted to make it a little bit more interesting. I don't know how many of you played Portal before. Okay, so hopefully many of you. What you have to know is that in Portal there is if somebody didn't play it, it's a computer game where basically you have to escape from a laboratory. You have to solve little puzzles and then you can go to the next level. And in the meantime, there's this little bad guy, this GLaDOS. It's what's the name? Genetic life form and disk operating system. So that's the bad guy who's trying to kill you, in short. And it's really just a puzzle game, so no fancy stuff. But it's a really cool game. And I thought that it would be a great way to demo Iris, meaning in that GLaDOS is constantly, you have a little comlink between your player and GLaDOS, and GLaDOS is constantly sending you nice wishes. And how that, okay, let's do that, simulate that comlink between our player and the operating system. And so what we could do is with this GLaDOS, same way we connect to the network, and then start publishing on an official channel, basically on an official comlink, some nice wishes. I hid the wishes there. I just generate a random wish and shove it out to the player. And basically this is, I just keep publishing the messages every 5 seconds at a time. And what I can do with the player, okay, let's run this one. And what my player will do is, again, same thing, connect to the network, but then, oops. Yeah, sorry about it. I think I actually ran the wrong code. Yeah, I linked to the wrong page. Sorry about it. So this is what I wanted to link to. So we start with the GLaDOS, and at our player side, again, connect to the network, and we subscribe to this official channel. Okay, we can subscribe to multiple channels, but let's just subscribe to the official one now. And echo whatever comes through. And if we start that one, and tuning in, GLaDOS should send us a message every 5 seconds. Yeah. I'll stop this now for a moment. Oh, sorry about it. Yeah, so a nice message from Portal. I read it just for the fun of it. That remember when the platform slid into the fire pit and I said goodbye, and you were like no way, and then I was like, we were pretending we were going to murder you. That was fun. That was it was one of the, I tried to collect a few of those GLaDOS nice quotes, and if you just run it, then you will get a lot of different quotations from GLaDOS. Okay, let's kill this. So this is how you can do completely decentralized publish and subscribe model through Iris. Basically, you can just subscribe to a topic, whatever topic you want, and then with another entity in the network, you can just publish to that topic, and all the subscribers will get it. Now, I wanted to show you a fourth communication primitive, the tunnel, but I won't show it to you now because I'm running out a bit of time. But I have some other stuff to show, some fancier stuff. So the tunnel is if you want to implement, for example, database transactions, the presentation will be available online. You can download it, you can play with it. The codes will be runnable too. So that one I won't show you. Basically, you can set up something very similar to a TCP stream where you can send and receive messages. But so these were, not a surprise. So how does this all work? I told you that I won't go into the details, but I included just this small slide. That's what Iris does internally, is that on each machine, virtual machine, host, you name it what you want, we run a simple Iris node, and you can connect with all these little client applications to that single node. And with the nodes will basically act as gateways, as routers for your messages between each other. So in our demo presentations, each of our web browser, web servers were one of these little green balls. And each were, when I said that I promise you that I will tell you what this 555 is, basically it is the access port of the local Iris node. And what these Iris nodes will do is basically they will automatically scan the network for other Iris nodes and set up a secured, encrypted communication pathway between them. And if you're really interested in what the Iris protocol is based on, it is based on pastry and scribe. So two of Microsoft's, one of them is a distributed hash table, and the other is a group communication framework. Well, not framework, sorry, group communication set of algorithms, so to say. Yeah, sorry. So these, all the details, you can find it on the website. You will have the link later. I don't want to go in it because it will be very long otherwise. So these were really just 4 communication primitives. 3 I showed you, the 4th I only described. And I just wanted to show you that you can really assemble really fancy stuff out of these. And one of the fancy stuff is that many people always say that networking is not visual, and whenever I try to show off with to anybody who's not related to computer science, then they always look at me that, yeah, so you did that in 3 years, and yeah, okay. So I figured that, okay, make it visual. And so I took Intel's Embry ray tracer. It is a really fast ray tracer that runs on machine. I don't know if everybody knows what a ray tracer is. You can get really nice renderings of physical renderings of scenes. And so I wanted to distribute that on top of Iris. So what I did is I converted the Embry's ray tracer into a tile tracer, meaning that the tiles are, so not the whole scene is rendered at once, but only individual tiles. And if I were to render the Austrian crown, which you have the copyright somewhere here for, then this would be on the kind of the speed of the rendering on an 8-core virtual machine in Google's compute engine. So here there's nothing really to render, but it doesn't progress in too fast. But if I just go in there, then you will see the speed that, okay, it's not a trivial task. So that is the base speed of Intel's Embry renderer. This is a 1 megabyte picture with 266 samples per pixel taken. So this is the base speed of the Intel's Embry renderer. But if we put this whole thing on top of Iris and distribute it onto 48 virtual machines on top of Google's cloud, then we have a little nicer rendering speed. So the whole distribution for this is, give or take, 50 lines of code. And if you really want to go into the details of those 50 lines of code, sorry, I'll go back a bit. Yeah. Then those 50 lines of code, the main thing is a request and a reply, and the rest is boilerplate. Okay, crap. So basically, with 50 lines of code, I could distribute it. I could distribute Intel's Embry ray tracer onto, let's say, arbitrarily many nodes. I would say I only tried 50 because it was getting expensive. So this rendering cost, okay, not the rendering itself, but setting it up and just trying everything, about $25. So yeah, that was enough for this little experiment. Okay, so intermezzo over. Now, let's say a more realistic service, because this was just a nice application, just something to show off with. Okay, I have 10 more minutes. Cool. So if I want to make a more realistic service, then let's say that imagine that you are visiting Gopher in Gopher Town. You've never been there. You have no idea what to do. And okay, you know that you want to look around. You know that you want to visit you want to have a coffee because you're tired, you're jet lagged. You want to take a walk in a park. Maybe you're interested about cultural events. Okay, something like that. And you have absolutely no idea where you can find such things. Well, Gopher Town has a really nice solution for you. It's called Grand Gopharium. Basically, it's a Gopher library service. And what it will do is that you can just go to the receptionist, describe that, okay, what you would like to do, what you're interested in, something like that. And then the receptionist will run through the library, gather all the things that you might be required in, and then give it back to you. And yes, you could just use Google for it, so to say, or your little Gopher could use Google for it. But then it would, all the information would be, you would have to piece together the information. We want our library to piece together the information automatically. So how hard could it be to organize such a library service? Well, actually, both easy and hard. So if I want a really simple version of our library, what we could do is that we have our visitor Gopher there, the swimming thingy. And we have our one single receptionist and our librarian. And whenever our visiting Gopher asks something of our librarian, then the librarian will run to our receptionist. Receptionist will run to the librarian, ask all the information, run back to the visitor and tell him all the information. This, you could describe this as the librarian being a web server and the receptionist being a web server and the librarian being a database and the visitor a browser, but let's stick to Gopher. They're much nicer little critters. Okay, but what will happen, you can do this simply, even without Iris, with use classical normal networking. Okay, but what happens if you have a sudden surge in visitors, or maybe your receptionist goes home sick? Well, library will crash. So what you would like to do is have multiple librarians and multiple receptionists going around in there. And then whenever we don't really care how many visitors we have, we just tell the first librarian, we don't care whether it's the blonde librarian or the brunette. Okay, maybe we do care, but that's beyond the point. But okay, the first librarian that comes, first receptionist, sorry, I keep mixing them up. First receptionist that comes, we ask her that, okay, can you please sort this out? Yes, of course. She will run back and sort it out, bring back the information. Okay, this is getting fancier. You could, if you wanted to solve this with classical models, then you could throw in some load balancers. That's complicated furthermore. What happens if our Grand Gopharium wants to extend from Gopher Town to Gopher Land, and basically want to introduce multiple departments? Well, it gets fancier. Because let's say that we introduce, we have the Gopher Town collection of books, but we also have a collection of burrows and tunnels. And we really want to have them separately in separate departments, otherwise whenever we want to renovate one department, everything comes crashing down. So if we decide that we want to burn the books in the burrows and replace them with new ones, then we don't really have to touch the Gopher Town collection. So we'll just have them separately in separate departments. But then it would be nice if we would have some management. Okay, I only drew here one Gopher, you could have as many as you want, that would oversee the whole thing. What's the point of overseeing the whole thing? Well, if, for example, we close down the burrows for a moment, it would be nice if the library would know about it. And also, if a visitor comes, the visitors won't have any idea what department the library has. So it would be nice to have somebody to ask them and be able to answer it. Yes, you could ask the receptionist, but let's separate the concerns for now. So this way, what we could do is that each gopher will, whenever he arrives at work, he will send a message to the boss that, okay, boss, I'm here. And whenever they leave from work, they say that, okay, bye-bye, I'm sick or I'm off to home. And this way we have a really dynamic service that whenever a department comes online or a department disappears, the whole system can notice it. And our little visitors can query the library of the departments and then query of individual interests. Okay, but what happens if our collection, so this way the library works. It's a working model. Yes, but we would like to actually introduce new books to the library. Okay, let's do that. Well, we can introduce a bookstore, let's call it Gopher Books Incorporated, and have a salesperson periodically, let's say every week, just go to the store, buy all the books that's on Gopher Town and the boroughs, and just get it to the librarians. It is fairly simple, but it is one more component that our library service would need to be able to work, to function in a real time normally. Okay, so this way we would have an up-to-date collection about anything that's described in the books. But what happens if we have, let's say, events that are not described in books, that you cannot read up on the next open source conference, you won't find it in any books, so it would be nice to somehow be able to find those too. Well, what we could do is actually accept suggestions from visitors. So whenever a visitor comes and he says that, okay, I heard about this little cool Gopher burrowing contest, then the library will say that, okay, that sounds interesting. So if you said that there's a contest, we'll hire an explorer or an arbitrary number of explorers, and we'll tell them that, okay, find out about this thing. Then our little explorers will run out, go to for example, Gopher News Incorporated, gather all the information that they can find about that thing, and then if it's worthy, then come back and incorporate it into our library. And if I were to just summarize this whole service, this whole library service, it would look like this, with all the communication pathways. So I have our visitors Gopher, they talk only to our only to the receptionists. The receptionist talk to the boss, talk to the librarians, talk to the explorer, and each Gopher is running around and doing its business. And if you wanted to implement this one with classical services, then you will have a hard time. And the reason is because you have really a lot of communication pathways, a lot of places where you would need load balancers. I can have, out of all these Gopher groups, there can be arbitrarily many. So if I want to load balance between them, I would need to put a load balancer in front of every single group, and I would need to maintain the state of those load balancers, and yeah. So it will be really, really ugly fast. And this is the nice part of Iris, that you can keep all these natural communication pathways as they are. You don't have to care. You don't care about any network complexities. So whenever, for example, our librarian receptionists want to ask our librarian about the boroughs, they will say that, okay, boroughs librarian, please respond to this request. And the system will get that request to the correct librarian will reply. Okay, if I want, for example, our new events to be explored, I can say that, okay, receptionist says that explore this new event. Explorer will say, okay, I will explore it, will run out. The exploration will take, 5 seconds, 1 hour, 1 week, whatever. And after he comes back, he can notify the librarians that, okay, I found some really cool contest, burrowing contest or tunneling contest, and here are the details. And then he can simply broadcast this to all the librarians. Then immediately all the correct librarians will receive it. If the burrowing contest is in let's say, Gopher Town, then obviously he will only broadcast to Gopher Town librarians. If it is in the boroughs, then he will broadcast to the boroughs. And basically, if you look at all these little arrows, if you have two-way arrows, then it means it's a request reply. If it's a one-way arrow, then it's a broadcast. So what I wanted to show you is that with these really two very, very simple components, broadcasting and request replies, on top of Iris, you can implement a very, very trivial, it's not really trivial, not really complex, let's say a nice little service. You can implement a nice little service very, very easily. So you can keep all the natural communication flow. You don't have to complicate it with technological features. And this was basically what I wanted to design Iris for, that it should be really, really trivial, simple to create distributed web services, decentralized web services that, okay, they probably can fail, but it's much harder for them to fail. And if you're not really convinced about my little academic Gopharium library, then then let's make it a little nicer. We can replace our bookstore with OpenStreetMaps. We can replace our Gopher News Incorporated with Facebook. And we have a nice, if I have internet connection, okay, so I don't have internet connection, never mind. I'll show it to you on a different window. Basically, we have a nice little online service, library service that basically so the whole design that you saw previously there is up and running live. And so you as a, let's say, visiting Gopher can just take this up. You can select that you're interested, for example, in okay, so internet. Check it. If you have internet connection, be my guest, readyourrank.com. It is live. So what you can do is basically you can check out all your interests that you're interested in. For example, you're interested in green spaces or water sites. You're interested in restaurants. Yeah, somewhere right here. You can check restaurants. If you would have internet connection, that something actually would happen. And then you would get a nice little heat map of all the places of interest to you. You can zoom in, you can check all the details. So basically, the Grand Gopharium online. Thank you very much. One more question, one more thing before I ask questions. If you access it from your phone, it will probably eat up quite a lot of memory. Just okay, parentheses closed. Questions, anyone? Yes?
Are there any benchmarks of how many messages you could pass through the system before it kind of becomes too much?
Actually, yes. So if I was running some tests on actually on Amazon and Google Cloud too. If you, I don't know the numbers by heart. If you have this little website there, I don't know where my mouse is again. Anyway, so you have the website, the bottom link.
Yeah.
And there you have a paper section, and first paper on it is at the end you will find the benchmarks. So you have the separate benchmarks for request broadcasts. Okay, I don't have fancy presentations now on it, so I won't show it to you, but you will find all the details online. Yes?
Who has credit for the Gopher drawings on your presentation?
The drawings are the official Gophers from the, actually you can find all the Gophers inside the Go source tree. Okay, almost the ones. The house is my drawing, and yeah, that's also a little bit modified with the books in his hands. So that's also not completely official. The rest are official. Yeah, and the books are from one of the previous Gopher talks, Go talks. So those are all the credits.
I think they were actually the C++ spec.
Okay.
They were being transferred into a furnace.
Yeah. Okay, so whatever you didn't burn there, we collected it. None.
Okay, so if I lose the cluster connectivity, whatever, I lose the message as well.
Yes. So actually, this was one of the main points that I tried to figure out initially, whether to go with this advanced message queuing protocol way and really try to make it bulletproof, or try to make it simple and more natural. I opted for a simpler way because the problem is that, okay, if I lose a message, then what happens? Because if it was a request reply, if it was a request, then yeah, I can lose it. But if it was a reply, then only your application will know whether you can lose it or you cannot lose it. So on application side, you will have a timeout, and then you can decide whether it was a sensitive operation and you actually want to check whether it succeeded before trying again, or if it wasn't a sensitive operation, just a simple web request, then yeah, shoot away and repeat. So that's the reasoning why I didn't opt for persistency.
Great. We're out of time now. But, thank you very much.